So there's a few things going on with this one. We have that fraction bar across there, of course, means we're going to divide, but it's also an enclosing symbol. It separates the top of the problem from the bottom. So we're going to start with the top. What are we going to do first up there?
We are going to parentheses, but the line there is basically a form of parentheses saying you have to do the top.
Yep. So once we're on top, what do we have to do up there first?
3 times 7, which is 21.
3 times 7, good, that's 21. Then what?
Then 21, or 8 plus 21.
Okay, and that makes?
29 minus 1 is 28.
Okay, so 29 minus 1 is 28. Now we can move to the bottom. On bottom, what do we have to do first?
6 times 4.
Okay, 6 times 4 is?
28.
24. And then?
5 times 2, which is 10.
5 times 2 is 10.
Then 24 minus 10.
Okay, 24 minus 10 is 14. And finally, 28 divided by 14 is 2. Okay. Anybody have any questions on that? Okay. Okay, well with that then we can transition into our new stuff. Tonight we're going to start adding in the algebra. So we're going to be looking at variables and how they work. There are a lot of different uses for variables. In any of those uses, it stands for an unknown number. In some cases, it can stand for any number. For example, in a formula like this, the P, R, T are all variables. And those are numbers that we can select from a situation and put in there and apply the operations to them. In other situations, like this one, it's still representing an unknown number, but we cannot put any number that we want in there for it. It has a definite value, we just have to figure out what it is. And tonight we're going to look at both of those uses. One of the most difficult things in math, and when we bring in the variables, I think it's probably the most difficult thing for quite a while, is taking a situation or taking words and putting them into symbols, and mathematical symbols. We have something like a number increased by 7. How would we put that into mathematical symbols? X plus 7, n plus 7, whatever letter we wanted to use for that unknown number, right? However we wanted to write it. Now there are a lot of other ways that n plus 7 or x plus 7 could be represented. We could have the sum of a number and 7. We could have 7 more than a number. And I'm not going to go into all of them. These the obvious ones like a number plus 7 or whatever. I wanted to get to this last one here because it can be a little confusing. 7 more than a number, is that 7 plus x or x plus 7? Well, the short answer is it doesn't matter. When we're adding x plus 7 and 7 plus x mean the same thing. They're going to come out to the same result because when we add, we can change the order of the numbers and we'll get the same result. But technically, if we're looking at the language here, 7 more than a number means 7 is being added to something. So we're adding 7 to that number. The only reason I bring that up is when we get to 7 less than a number, is that 7 minus x or x minus 7? In this case, it does make a difference. When we're subtracting, you cannot change the order of the numbers. It will affect the answer. So which one of these is correct for that? X minus 7. It is 7 less than a number, which implies that 7 is being taken away or 7 is being subtracted from another number. And of course, there are all sorts of ways that that can be expressed. A number decreased by 7. Or the difference between a number and 7. All would indicate subtraction. Now, one that is closely related to this one, this first one, looks very similar to it, would be this. What's the difference between that one and our first one up here? The word than, right? And what was that?
Would be 7 minus x.
Perfect. This is 7 minus x. 7 less a number means you're taking the number from 7. 7 less than a number means you're taking 7 from the number. So that's one of the reasons why it is so difficult to take the language and put it into a mathematical formula, is because there's so many small subtleties like that that you have to be watching. We could run into things like the product of a number and 3. How would we write that? Well, first of all, what operation is that indicating? Multiplication. Product means multiply. So the product of a number and 3, let's use y for our number. Y times 3 or 3 times y. Most of the time, even though either one would be correct, when we're dealing with algebra, we tend to write, not only do we put the number first, but we leave out the multiplication and just write it as 3y. A little warning in my math lab, by the way. Since it really doesn't matter whether you use x, y, z, w, n, or whatever for that missing number. But in my math lab, watch closely at the very bottom of the problem, right down by where you're going to put the answer into the box, it will say use w for the number or use x for the missing number. Make sure you do that or my math lab will count it wrong. I mean, it's a computer program, which means it does have those little bit of built-in stupidities to it where it can only recognize certain things. That's one of them. So we can have multiplication like that. Division, there's also several ways that can be put in here. Let's say we have a number split 5 ways. Of course, that's going to represent division. Could be n or x or whatever divided by 5. But again, in algebra, just like we shorten up the multiplication, we tend to write division in the form of a fraction. As n over 5, like that. Where it gets trickier, the simple single operations aren't so bad. But where it gets trickier is when we have combined operations. For example, seven times the number increased by 4, or 7 times the sum of a number and 4. Let's look at the first one here. How are we going to write that out with symbols? 7x plus 4. Good. 7 times the number, 7x, increased by 4, plus 4. How about this second one? At first glance, you might want to say that it's exactly the same, but it's not. This one was 7. Okay, there you go. Keep going.
7 parentheses x plus 4.
Perfect. This was 7 times a number. 7 was just multiplying that missing number, x. This is 7 times the sum. The sum is the result of an addition problem. So it's implying that we've already done the addition and we're multiplying that result by 7. Towards the end of the class tonight, we're going to throw out some word problems and we'll practice pulling the information out of word problems a little bit more of a realistic setting rather than just the number phrases like this. But as I said, at this point, for what we're going to learn, this is probably the single most difficult skill in this course, is taking words and putting them into a formula. once we have the formulas, the algebraic numbers, how do we work with them? Well, we touched on this a little bit last week of something like 7x is just like any other number. It has its two parts. 7 is the count, telling us how many, just like having 7 inches or 7/10 or any other number, any other form of a number. And x is the name. So we could take 5x plus 3x, and what are we going to get? 8x. Good. Because whenever we add numbers, we combine the counts. 5 and 3 make 8, and we keep the same name. If we had 7y plus 9x, what do we get? Yeah, 7y plus 9x. Because they have different names, we cannot combine those with addition or subtraction. Now looking at this one, we have different names, but there are still things that we can combine because there are some digits that have names in common. The 5x can be combined with 9x. They both have the same name. So if I combine those, what do I get? 14x. And the 3y can combine with the 2y to give us 5y. Now I have to be careful here right now. At this moment, there's something missing here. Can anybody tell me what it is? I need to connect those together somehow. I can't just have 14x and 5y sitting there. I have to have an operation. Since this is a positive 5y, we connect them with a plus. It won't always be positive. So here, there are things we can combine. Tell me what to combine.
7a plus 4, or 3a, sorry.
Well, 7a, and is this a 3a?
This is a negative 3a.
It's actually a negative 3a. So 7 and negative 3 will give us 4a. Then we have 4b and negative 11b make negative 7b. Now in that case, since it's a negative 7b, there's already that negative sign there. And that serves to connect them together. It's 4, and you can think of that either way, is 4 minus 7b or 4 and a negative 7b. It behaves exactly the same, and depending on the situation, it's easier to think of it one way or another. But we can move up from there. We can have more than one digit. Each of these is a single digit number. And just like we have in whole numbers, we have place values in our algebraic numbers. 538 really represented the number 5 hundreds, 3 tens, and 8 ones. Well, the same is true for an algebraic number. A lot of people look at this and they see 3 numbers, but it really isn't. It is a single number with 3 digits. The difference is our place values have changed. Instead of having ones, tens, hundreds, and 1,000s, and so on, we have the ones digit, the x's digit, and the x squared's digit. This number will behave exactly the same as that number. If I take like 3x squared plus 5x plus 9, and I'm putting in parentheses not because I want to do anything there first. I'm just trying to separate it from the other number. Plus 4x squared plus 7x plus 2. Now, many of us were taught a shortcut where you just drop the parentheses and combine like terms. But technically, this addition happens exactly the same way as our addition with whole numbers. Just like with whole numbers, I would line up the digits that have the same place value. So the x squareds are going to line up with the x squareds, and the x's with the x's, and the ones with the ones. And I'm going to add. Now, it doesn't matter what direction I go, but just to be consistent with whole numbers, I'll start on the right and work my way back to the left. 9 plus 2 is 11. So that's a positive 11. Now, here's one of the big differences between the algebraic numbers and the whole numbers is we don't carry with algebraic numbers. There's no place to carry that extra 1. So we can have a 2-digit number or a 3-digit number in each place value. 5x plus 7x, 12x. And again, that's positive, so it's a plus. 3x squared plus 4x squared, 7x squared. So the process is just like with whole numbers. Now, we already saw one major difference in the fact that we can have 2 digits in the same place value. We don't carry with our algebraic numbers. The second major difference we have from our integers and whole numbers is in a whole number or integer, every digit of the number is either positive or negative. The 538, that is a positive 500ths, and a positive 3/10, and a positive 8 ones. If I have a negative 273, that is a negative 200ths, and a negative 7/10, and a negative 3 ones. Every digit of the number is either positive or negative. In an algebraic number, each digit can be positive or negative on its own. We can have 7x squared, negative 3x, and a positive 11. So when we're working with our algebraic numbers, we have to deal a little bit more carefully with the integers, the negatives. We might have 5x squared plus 7x minus 13 plus 9x squared minus 12x plus 4. And again, we're going to line them up. As I said last week, if you have a method you've used before that works for you, don't feel like you have to change to do it my way. I know most of you are taught just get rid of the parentheses and combine like terms. If that works for you, feel free to keep doing it. I just throw out my different way because it sometimes helps. So anyway, here now, we're still adding down each column, but we have to deal with negatives in each digit. So negative 13 plus 4, negative 13 and positive 4 makes negative 9. Good. 7x and a negative 12x. We have a positive 7 and a negative 12 will give us negative 5. There we go. Negative 5x. And 5x squared and 9x squared is 14x squared. Any questions? Where the negatives get to be more complicated is when we start dealing with subtraction. So we'd have 5x squared minus 7x plus 4. Subtract 8x squared plus 4x minus 9. Just like before, we're going to line up our columns. And this time, however, we're subtracting down each column. So we have 4 subtract a negative 9. If you recall your rules of integers, 4 minus a negative 9 becomes 4 plus 9. This is a positive 13. Negative 7 minus 4. Negative 7 subtract 4 becomes negative 7 plus a negative 4, otherwise known as negative 11x. Perfect. 5 minus 8, negative 3x squared. How many of you have problems with the negatives? Is there anybody that wants me to go over the negatives a little bit more before we move on? A little bit? Okay. When we're dealing with the negatives, the one thing is, remember from last week we had mentioned you don't ever want to subtract with negatives because it's really confusing. So each of these, you'll notice I wrote it as a problem off to the side just so that I can make the changes. Change it to addition. Something like a negative 8 minus 13. I'm going to change that. The subtraction means add the opposite of whatever follows it. So the negative 8 doesn't change, but this becomes plus. The opposite of a positive 13 is a negative 13. And once it's in that form, it's negative 8, negative 13, has to be a negative 21. We might have 7 minus, negative 9. Again, this subtraction means add the opposite of what follows it. So it's be 7 plus, well, the opposite of a negative 9 is a positive 9. So that's just 7 plus 9, or 16. I'm going to leave it at that for now. If you have more problems with negatives, let me know. Bless you. Have more problems with negatives, let me know. And I'll either help you with it one-on-one or I'll make a video for you that you can watch, whichever is easiest for you. I realize with this once-a-week class, it's kind of tough to get to me sometimes. So anyway, let's have you guys try one of these. Subtract those quick and see what you come up with. Let's see how you did. Starting from the right and working our way back to the left, we have negative 13 minus 8 is negative 21. Good. 11x minus a negative 5x. Positive 16x. Good. And 5x squared minus 9x squared. Negative 4x squared. Perfect. How many of you got that? Perfect. Now, many of you are probably taught when you're subtracting, you're going to take out the parentheses and change the sign of everything in the parentheses, then combine like terms. Again, if you have a method like that that you use that works for you, feel free to keep using it. I'm not going to stop you. Well, our next step is to look at powers and multiplication. We briefly looked at something like this last week. What does that mean? 8 to the third power. 8 times 8 times 8. Has everybody figured out how to do that on your calculator, by the way? Depending on your calculator, you'll have one of 3 keys. Most of the Texas Instruments have that key, called the caret key. Some of the older Texas Instruments have an X to the Y or Y to the X key. And a lot of the Casios and Sharps and some of the newest Texas Instruments have like an X to a box or something like that. All of those keys work the same way. You would type in 8, press that key and hit 3, and it should spit out 512. Everybody get it to work? Okay. Try one more. 5 to the power of 6. See if that one works for you. You get 15,625? Perfect. Okay, so with the numbers, we can deal with the powers. But what happens if we have a variable with a power? Just like 8 to the third means 8 times 8 times 8, of course, x to the third is x times x times x. We saw a little bit last week that x times x, of course, just equals x squared. But what if we have something like this? X to the fifth times x to the third. Well, x to the 5th from what we just saw is 5x's multiplied together. X to the 3rd is 3x's multiplied together. If we multiply them together, what do we have? X to the 8th. We have 8x's now all multiplied together. As you can see, the net result, or the shortcut, would be just adding the powers. 5 plus 3 is 8. So if I have y to the 7th times y to the 11th, I'm going to get y to the 18th. Good. Z to the 15th times z z to the 16th. Perfect. Whenever we have a variable without a power on it, it's really a power of 1. We just don't bother writing it in. So it'd still be 15 plus 1 is 16. So now we can start looking at this. Again, we looked at something simple like this last week. When we multiply numbers, we combine counts, but we also combine the names. So here we're going to multiply, we're going to combine 8 times 3, which is 24. But we're also going to combine the names. X times x, as we said, is x squared. Well, we can deal with higher powers now. We can have 5x to the 6th times 7x to the 4th. Same as always, we combine the counts. 5 times 7 is 35. Then we also combine the names. X to the 6th times x to the 4th is x to the 10th. When we're multiplying variables with powers, we add the powers. So for this one, same type of thing. We're going to combine the counts. What are we going to get over here? Negative 12 times 3 is negative 36. And then we'll combine the names. X to the 5th times x squared is x to the 7th. Very good. What if we have different variables? Can we combine them? Well, with addition or subtraction we couldn't, but with multiplication we can. We do not need the same name to multiply. 5 times 7 is 35. We combine the counts, and then we also combine the names. X times y is xy. We can run into something like this. And still, we're going to combine the counts. 13 times 2 is 26. And then, just like x times y became xy, x to the 5th times y squared is just x to the 5th y squared. Or we can have the variable appear in each term. Still going to combine the counts. 4 times 7 is 28. And then when we combine the names, we can combine each of them separately. X to the 3rd times x to the 4th is x to the 7th. Y times y to the 3rd. Remember, that's really y to the 1, so this will be y to the 4th. 1 plus 3 is 4. But we're not just combined to having single-digit numbers. We can have multiple-digit numbers. We might have 5 times 3x plus 7. Just like when we did something like 3 times 24. We set this up as 24 times 3. We did 3 times 4 and then 3 times 2. This works the same way. Now I realize you guys have been taught some shortcuts and we'll look at that in a minute. But the full way or the complete way of doing this is 3x plus 7 times 5. And just like we would with our whole numbers, it's 5 times 7 is 35. Positive, so we put a plus. The difference is we don't have to carry anything again. 5 times 3x is 15x. Or something like this. 7 times 8x minus 3. It's 8x minus 3 times 7. Now this isn't 7 times 3, it's 7 times negative 3, so we're going to get negative 21. Then 7 times 8x is 56. Oops, I forgot the x there, didn't I? So it is 21x. 7x times negative 3 is negative 21x. And 7x times 8x is 56x squared. Sorry about that. Now, most of you were probably taught a process called distributing. Distributing is nothing more than a shortcut of this long multiplication. It saves room and a little bit of time. So when you see something like this, you're probably taught to take this 5 and do 5 times 3x is 15x, and 5 times positive 7 is positive 35. We get the same result. It's just a little bit shorter way. It takes a little less paper. And the same down here. Take 7x times 8x is 56x squared, and 7x times negative 3 is a negative 21x. From here on out, you're going to see me doing the distribution just because it saves time and space. I just wanted you to see this so you can see what really is going on behind the scenes. It's just long multiplication. And just like with our whole numbers, we can run into order of operations problems. This here looks very different, but it is really a similar problem to 7 times 8 plus 4. On this one up here, we would multiply first and then add the 4. The same is going to happen down here. So our 3x times the 5x minus 2 will distribute. So 3x times 5x is 15x squared. 3x times the negative 2, negative 6x. And we still have the 9x to add down here. Where can we combine that? Where can we add in that 9x? With the negative 6x. Technically, we could move it down here if we wanted to. Negative 6 plus 9 is positive 3x. So 15x squared plus 3. I'm going to have you try this one in your seat. So where would we start? Perfect. So 5 times 7x, 35x. 5 times 2 is 10. Careful, not distribute. We're just going to combine the 4x with the 35x. The 4 is outside the parentheses, so it's not going to be touched by this 5. So 35 and 4 make 39x. Still just x, because at that point we're adding. Plus 10. So let's look at this one. Tell me what to do. So we're going to distribute on both sides. We'll start here. 7 times 3x, 21x. 7 times negative 5, negative 35. And over here we're distributing 2 times 7x, so positive 14x, and 2 times 2, positive 4. And now we're just combining the things with the same name. We're combining like terms. 21x and 14x combined to make 35x. Negative 35 and a positive 4 make negative 31. Any questions so far? Okay. What if we have two multiple digit numbers? So far this was a single digit number times a 2-digit number. What if we have something like that? Now most of us have been taught a process called FOIL, first, outside, inside, last, which again is a shortcut. This can be done using simple long multiplication. If I had 27 times 43, I would do the 3 times 7, then the 3 times 2, and so on. Well, the same could happen here. Take my 3x plus 2 times 5x minus 4, and I can do my long multiplication. Negative 4 times 2 is negative 8. Negative 4 times 3x is negative 12x. Now, just like with whole numbers, we'd leave a blank spot or put a 0 in here. We're going to do the same before we move over to the 5x. 5x times 2 is 10x. Positive, so I'm going to put a plus there. 5x times 3x is 15x squared. And you can just combine the columns. Negative 8 and 0 is negative 8. Negative 12x and positive 10x is a negative 2x. And 15x squared. So you can see it's the exact same process as with our whole numbers. That's one of the reasons why I wrote out the whole numbers in that long form with the place values in it when we did these. Because you can see exactly what's going on here. Now, like I said, I realize that most of you were taught FOIL. So if I have 3x plus 2 times 5x minus 4, FOIL simply meant F stood for first. You multiplied the first digit in each of them. So 3x times 5x is 15x squared. O stood for outside. 3x times negative 4 was negative 12x. I stood for inside. The inside two digits, 2 times 5x is 10x. And L stood for last. The last two digits, 2 times negative 4 is negative 8. And then you had to combine like terms. The negative 12 and the 10x make a negative 2x. So we still have the 15x squared and the negative 8. You can see we get the same answer. Again, whatever method has worked for you in the past, feel free to keep using it if you're comfortable with it. Last thing to throw in here before we hit our break is just some simple division. 8x divided by 4. Well, when we multiply, we just combine counts and then combine the names. When we divide, we do the same. So we're going to combine the counts. 8 divided by 4 is 2. Now there's nothing to divide the x. It just stays x. Think of that just like if we had 8 inches and we're dividing it into 4 equal pieces. Each piece is going to be 2 inches. The name does not change. However, we do have variables that we're divided by. We do have names that come into play. We can divide the counts. 27 divided by 9 is 3. And then also divide the names. When we were multiplying with the powers, we added the powers. When we're dividing with our exponents, we're going to subtract the powers. So this is x to the 4th. Technically, that is x to the 1. So 4 minus 1 is 3. So x to the 3rd. Or you might have 48 x to the 7th divided by 12 x to the 5th. Try that one really quick in your notes. So what are you going to get for the number? 4x squared. Perfect. Any questions? Technically, we're like 3 minutes early for our break, but let's take our break here. We'll come back at 6:28 and we'll start up again.